Good morning. In this lecture, I am going to discuss about the steady state error and static error coefficients. Now, uh, so far we have discussed about the transient response, transient characteristics, transient response characteristics. That means your TR, TP, percentage MP, and settling time. So, when the oscillation is actually coming into the state where there is no oscillation or very minimum amount of oscillation with respect to your input value, that means your desired value. See, this is your time response for any second order system. If we consider this like so, this portion we may consider as the steady state one. So if you see in the graph, you can see that this part is your settling time. That means up to this can be taken as the transient part, and next this is your steady state part. So when it reaches the steady state, what happens? There may be difference between the input or output, or there may not be. So this is your actually output curve, and see this is your input curve. So when the curve reaches at the steady state position, there will be certain error, right? So error means the difference between the input signal and output, or you may take it as the desired signal minus obtained signal. So that is your error, as we know already. And in some cases there may be some error. That means E of t can be like C of t in time domain, and there may be some cases where the steady state error may be 0. That means this can be 0 or maybe positive value. So for any actually for any control system which is accurate or more efficient, that means the steady state is close to 0, this very much close to 0, or the design is to be made in such a way such that the steady state error may be approaching to 0. So first of all, we have to know what is the expression for steady state error for any kind of system subjected to any kind of input. That means we have to find out steady state error. Steady state error means t tends to infinity, or for the final value theorem, what we know, this equal to in Laplace domain can be written as s into es. So now onwards we will call steady state error ess equal to limit s tends to 0 s into es. Once you know the es for different types of inputs, what the different types of inputs available, that is your step, ramp, and parabola. Normally unit impulse is not taken to calculate the steady state error. What are the different inputs normally taken? That means your position, this is your velocity, and this is your acceleration. Already we have discussed it in detail. Now if this kind of inputs are applied to any system, this is your system, different types of inputs we are applying, we are getting the outputs, and corresponding to that steady state error. So this is not only depending upon the input. You see, this is your structure. So input is passing through the system to give you the outputs. If the different kinds of outputs is obtained for different types of input, that means there is a role of system. So type of the system is very important. If the type of the system varies, so again the outputs are varied, and accordingly you will get the different steady state error, right? So we will concentrate how to get the steady state error for different types of system as well as different types of inputs applied to that particular system. Fine. Now we will consider a basic block diagram of a control system. That is your RS input, this is your error block, this is your open loop transfer function GS, this is your output CS, and this is your feedback HS, right? So what is the signal coming here? See this part. as you see, this is your RS and this signal is CS. So here what is coming, that is CS into HS. So here you will get RS minus CS into HS, right? And this RS minus CS into HS is your error signal. This is your ES. Normally, in case of control system, many of the signals or systems is having HS is equal to 1. So this is known as unity feedback system. Already we are aware of about this. So ES, that is ES error, that is RS minus CS, right? Now this ES into GS will give you CS. So CS is your output, that is equal to GS into ES. Now if you can put the value of ES here, you get GS into RS minus CS, right? This can be one type of expression. Another what we could get, you see, so if you get the CS equal to GS into ES, so you write ES equal to RS minus, instead of CS we can write it as GS into ES. So ES, you take it in the left hand side, you 1 plus GS equal to your RS. So ES becomes simple RS by 1 plus GS, right? So this is your error signal in Laplace domain. Now what is your ESS? As you know from the final value theorem, S into ES, that means if you get the steady state error for any kind of system, what you have to do, you have to just use this notation. So what you will get, see the expression of ES, right? See, this is your RS, that means different types of inputs, maybe step, maybe RAM, this may be step, maybe RAM, maybe parabola, and this is the transfer function of open loop system. So there may be type 0, type 1, type 2 and so on. So once these are varied, and these can be also varied to get the defined steady state error for different types of signal. Steady state error means when you have reached the steady state region, so there may be having some error between the desired value and measured value. So that to be minimized by some other technique, but first of all you have to find out this steady state error by using this calculative method. General expression for steady state error is ESS is equal to limit S tends to 0 S into RS by 1 plus GS. Right. Now we will consider the different cases. Right. Say for example, in any case, any system, for any system we are considering for position input. This is known as position input, means the value of RS equal to 1 by S, that is your step signal, right? So what will be the steady state error? See, limit S tends to 0, the system remains same, S into 1 by S by 1 plus GS, or in general term you can write it like open loop system transfer function. I will just modify it like this, 1 plus GS into HS. So this can be HS here. So what is the term you are getting? That is 1 by 1 plus GS HS, and this is a function of S only, this part. See, so limit S tends to 0 can be applied only this part. So 1 by 1 plus limit S tends to 0 GS HS, and this part is known as position error coefficient. See, what is this? This is known as KP, that is limit s tends to 0 GS HS. So once you find out the open loop transfer function, put the value of s is equal to 0. In the limiting case, you get the static error coefficient. This is known as your static error coefficient. Once the static error coefficient, this is static position error coefficient, right? This is your static position error coefficient, because we are applying the position type of input signal, that is step signal. So steady state error finally becomes 1 by 1 plus Kp for what? For Rs is equal to 1 by S. That means your step type of input signal. So you get the expression for it. Now I am moving to the velocity type of input, that means ramp signal. But to Rs equal to your 1 by S square. That means your ramp signal is applied. So ESS equal to your limit S tends to 0 S into Rs by 1 plus GS into HS. So get limit S tends to 0, put the value of Rs is equal to 1 by S square, S into 1 by S square by 1 plus GS into HS. Limit S tends to 0, 1 by S into 1 plus GS into HS. So limit S tends to 0, 1 by S plus S into GS HS. Here you can apply this limit to this S and there also. So if you put S tends to 0, here you get 0. So 1 by limit S tends to 0, S into GS HS. So this is known as 1 by KV. And what is the value of KV? KV is known as the velocity error coefficient. This is your KV, right? So KV equal to limit S tends to 0, S into GS into HS, and this is known as velocity error coefficient. This is also one kind of static error coefficient. Now once you get the system of different type, you get the value of the steady state error according to the KV. That means for the given open loop transfer function GSHS, you just get the value of the KV, that means the velocity error coefficient. Once you get the velocity error coefficient for a particular type of system, you get the steady state error for ramp type of input, right? Next I will discuss about the third part, that means your Rs equal to 1 by SQ. This is parabolic type of input. Similar fashion, if I move, then you'll get S tends to 0, S into Rs by 1 plus GS into HS. Put the value of Rs here and you will get S tends to 0, S into 1 by S cube by 1 plus GS HS. So this will be simplified like 1 by S square plus S square into GS HS. So this will be 0, and finally this will be 1 limit S tends to 0, S square into GS into HS, like the previous one. And see, this may be written as 1 by Ka. Ka means this is your acceleration time constant, and this K is nothing but this term, right? So Ka equal to limit S tends to 0, S square GS into HS, and this is known as acceleration error coefficients. So now you know the different types of error coefficient. That means there are three error coefficients, and what are the values of that? That means Kp, that is for step signal, Kv, that is for ramp signal, and Ka, that is for parabolic type of input signals. And you get the three error coefficient, which are known as also the static error coefficients, right? Now we will discuss the application of the static error coefficient to find out the steady state error for different types of system, maybe type 0, maybe type 1, maybe type 2. We are considering a type 0 system. So you know, in case of type 0 system, there is no pole at s is equal to 0. So we may consider GSHS equal to like 1 by s plus 2 into s plus 4. See, there is no pole at s is equal to 0, right? So if this is your open loop transfer function of type 0 system, what happens if you applied different types of input? For example, first of all, you are applying input is equal to step. So when you apply the step signal as the input side, so what is the error coefficient you will get? That is your Kp, position error coefficient. What is that? That is limit s tends to 0 gs into hs from the previous part. So you just put this s tends to 0, 1 by s plus 2 into s plus 4. So you get 1 by 8 or 1.25. That is your some finite value, right? So what is the error? Error is 1 by 1 plus Kp, right? This is the error corresponding to step signal when the input is step. So you get 1 by 1 plus 0.125. So that is your finite value, right? You get certain value. Now next part, you see that is your input is RAM for the same system. Input is RAM. What will get for RAM? What you have to find out? You have to find out the velocity error coefficient Kv. That is again limit s tends to 0 as into gs into hs. Now put the value of this by s plus 2 into s plus 4, right? So what will get? This is finite, this is 0, so ultimately this will be Kv equal to 0. Once you get the Kv equal to 0, then you know the steady state error for RAM type input is 1 by Kv. So 1 by 0, that is infinite. So there is infinite error when the system reaches steady state, when the actually your system is type 0 system and input is RAM, right? Similarly, you can get input is parabolic. So you have to find out the static error coefficient Ka, that is limit s tends to 0 s square into gs hs. So this is again 0. So what else you get? That is the steady state error 1 by Ka, right? So 1 by 0 you get infinite again. So these are the three types of input applied to any kind of type 0. See, if the order of the system is third, so another factor was there. So then also by the same calculation you can see only the steady state error is finite for steps type signal. When you will apply the RAM type signal, you will get infinite error. When you will apply the parabolic input, you get the infinite error, right? So by this similar fashion we will discuss the type 1 system and type 2 system. This is type 1 system. Say GSHS type 1 can be written as s into s plus 2. You see there is a pole at s is equal to 0. So this is a type 1 system. Now if the system is type 1, again we will apply the step signal as the input, step input. So what is the value? That means error coefficient related with the step input, that is your Kp, that is limit s tends to 0 gs into hs. So what we get if you put s tends to 0 gs hs? So limit s tends to 0 1 by s into s plus 2, right? So put the value of s is equal to 0 here, well you will get 1 by 0, that is infinite. So you get the Kp, that means the static error coefficient is that is position error coefficient is infinite. So steady state value of error, that is 1 by 1 plus Kp for step type of input. If you put this 1 by infinity, that is 0. So for any type 1 system, if you apply step signal, you get the steady state error equal to 0. You say we are applying ramp type of input. So ramp type of input, and you see in that case static error coefficient is velocity error coefficient, that is Kv, that is your limit s tends to 0 s into gs hs, as you know. So put the value of s into 1 by s into s plus 2. What will get? This cancels out, so 1 by 2, that is 0.5, which is some finite value, right? Now if the value of velocity error coefficient is Kv, so what is the error? 1 by 0.5, that is 2, that is even finite. So in this case, when for type 1 system you are applying the ramp input, you are getting the steady state error finite, right? In this case steady state error was 0, in this case steady state error was finite. And in case of parabolic input, for parabolic type of input, the error coefficient is acceleration type of error coefficient, that is limit s tends to 0 s square into gs hs. You see, put the value, but you will get s square into 1 by s into s plus 2. So this will be equal to s by s plus 2. So this will be 0. So acceleration error coefficient for the parabolic type of input is 0. Then the steady state error is 1 by Ka, that means 1 by 0, again infinity. So for type 1 system, if you apply the step input, you will get the steady state error 0. When you will get the ramp input, if you apply the ramp input, you will get the steady state error is equal to finite. And in case of parabolic type input, the steady state error is infinite. This is all about to find out the steady state error for different types of input in a type 1 system. Next part I will discuss about the type 2 system. Next, type 2 system. Let us take some example of type 2 system. Gs into hs, open loop transfer function is equal to say s square into s plus 2. See, at s is equal to 0, 2 poles. That means this is a type 2 system. Now for type 2 system, first of all, step signal is applied. We will consider the case of step input, and so for that Kp equal to gs into hs. If you put limit s tends to 0, 1 by s square into s plus 2, what you will get? If you put this 1 by 0, that is infinite. Once the value of Kp is equal to infinite, that means es is 1 by 1 plus Kp, 1 by 1 plus infinite. So this is again 0. So you see, for step type of input, for type 2 system, you get the steady state error is equal to 0. Second part, for the similar fashion, you can apply the ramp input. For ramp input, you will get the Kv, that is velocity error coefficient. This is limit s tends to 0, s into gs into hs, that is limit s tends to 0, s into 1 by s square s plus 2. So this is limit s tends to 0, 1 by s into s plus 2, right? What we'll get, this is simply you get 1 by 0, that is infinite. Once you get the value of kv equal to infinite, so you get the your steady state error, that means 1 by kv equal to 0, right? And number 3, parabolic input. For parabolic input, you have to find ka, that is limit s tends to 0, s square into gs hs. So this will be s square into 1 by s square s plus 2. So it will be limit s tends to 0, 1 by s plus 2, that is 1 by 2 finite. So finite value of ka, steady state error 1 by ka, that is 1 by 1 by 2, 2. So you get this is the finite steady state error coefficient. Out the static error coefficient and finding out the steady state error for different types of system applied when the different types of inputs are applied to it. Now once you get understand about this, now you can solve a certain kind of problem. Now I am going to discuss a problem. Statement is given like a unity feedback system is characterized by the open loop system GSHS is equal to 1 by s into 0.5s plus 1 into 0.2s plus 1. Now there are two parts. You have to first determine the steady state errors for step type of input, ramp type of input and parabolic type of input, and the second part is to determine the performance characteristics in the in time domain, that is rise time tr, peak time tp, percentage peak overshoot mp and settling time ts when this system is subjected to unit step. So step by step I'm just discussing the procedure how to get the defined sections and then solution of this problem. See, first of all, steady state error for the step, you already having this open loop transfer function. Now in order to get the steady state error for defined types of input, what you have to do, you have to first find out the kp, that means for your step input. So when step input is applied to the system, what happens, so kp equal to limit s tends to 0, gs into hs. What is that? If you put this limit s tends to 0, that means s tends to 0, 1 by s into 0.5s plus 1 into 0.2s plus 1. Now putting this value of s, you get this is your 0. So this gives you infinite, right? So s is equal to 0 means in the denominator it will be 0, so this will be infinite. So steady state error for step input 1 by 1 plus kp, that is 1 plus infinity. So you get the steady state error is equal to 0, right? Similarly kv you have to find out for ramp type input. So limit s tends to 0, s into gs into hs. So what we will get, this will be your s into s 0.5s plus 1 into 0.2s plus 1. If you put the value of s is equal to 0, you get 1, that is kv is equal to 1. Once you get kv is equal to 1, 1 by kv, that is your 1. Steady state error is 1 in this case for unit ramp. And the third part is parabolic, and find out the acceleration error coefficient, that is limit s tends to 0, s square into gs hs. So that is equal to limit s tends to 0, find s square into 1 by s square into 1 plus 0.5s into 0.2s plus 1, that is your 1, that is again 1. So if the value of k equal to 1, sorry, this will be in the denominator, so this will be your s actually, so my mistake. in the numerator this will be s by, sorry, I can write it s by limit s tends to 0, 1 plus 0 0.5 s, 1 plus 0 0.2 s. Now you get this k equal to 0. If you get the value of acceleration and coefficient is equal to 0, so steady state error for parabolic type of input is 1 by ka, that is infinite. So the first part is over, that means determination of the steady state error for this system when defined types of inputs, step, ramp and parabolic types of inputs are applied. Now coming to the second part. In the second part, determination of the rise time, peak time and percentage peak overshoot settling time. To get these values, you have to first get the closed loop transfer function. So Cs by Rs equal to your Gs by 1 plus Gs Hs. So you get the value of this equal to, you see, this is your closed loop transfer function. So this will be you just put the value of s into 0.5 s plus 1 into 0.2 s plus 1 divided by 1 plus 1 by s into 0.5 s plus 1 into 0.2 s plus 1. So you get this is 1 by s into 0.5 s plus 1 into 0.2 s plus 1 plus 1. See the characteristic equation. What is characteristic equation? That means your denominator equal to 0, and this is a third order equation. This means this is a third order system. So once it is a third order system, so we don't have any relationship known to us that will give you TR, TP, percentage TS and percentage MP and TS, because these are the parameters we have calculated for unit step input when subjected to a system which is normally second order. So what to do? In that case, this third order, from this third order expression, that means from the characteristic equation, this is your characteristic equation, you have to find out the roots, right? First of all, you have to find out the roots. The roots, we have to get the characteristic equation, that means 1 plus GSHS equal to 0, and by using this formula you get s into 0.5s plus 1 into 0.2s plus 1 plus 1 equal to 0. After simplification you get s cube plus 7s square plus 10s plus 10 equal to 0. See, so this is a third equation, and if you factorize this, you can get like s plus 5.15 into, this is s plus 5.15 into s square plus 1.84 s plus 1.81 equal to 0. So there are two factors. One is first order factor. This is your first order factor, and this is your second order factor, right? So from this you have to find out whether this will be actually used to find out the TR, TP and percentage overshoot. That means you have to take the first order part or you have to take the second order part. Now there is a confusion. So in order to get the actual factor which is to be taken care, either first order factor or second order factor, you need to get the solution of it. That means if this part is solved, what you get, the pole at minus 5.15, right? And if you solve this, you will get the two poles which are located say by using the Sridhar-Acharya. So once you solve this by using the Sridhar-Acharya, you get the two poles, as this is the second order, and the poles are minus 0.74 plus minus J1.12. Now see this factor, first order factor having the real pole at minus 5.14, and this is the second order factor having the real pole minus 0.74, and these are the very two important observation you need to have. is at minus 5.51. That is the real part of the pole, and second one is minus 1.74 plus minus j 1.12, sorry, minus 0.74. That was, see, 0.74. So minus 0.74 plus minus j 1.12. Now this is the real part. Now if you plot the location, this is your S plane, location of the real part, location of the real part. So location of the real part, that is very important. So if this is say minus 0.74, so 5 will be located somewhere like this, right? So as the poles are located far away from the real axis, sorry, imaginary axis, that means these poles containing factor can be neglected. So the poles which is very close to origin or imaginary axis, say this is minus 0.74, which is very close to the origin, close to origin. So this is your dominant pole, right? So this is known as the dominant pole. So in any case, if you want to find out the defined factors, and out of the defined factors, how can you get the dominant pole? That means if the pole is lying very close to origin, that means the real part of the pole is lying very close to origin, and that is very close to imaginary axis. So that pole is taken to be dominant pole, and the dominant pole is here. You see, this is for the as a second order factor. So you need to have only the second order factor corresponding to that, and the second order factor corresponding to that is equal to s square plus 1.84s plus 1.81 equal to 0. So now you have obtained your denominator part, that means s square plus 1.84s plus 1.81, and if you get this from this, this is your omega n square. So omega n square comparing is 1.81, and 2 xi omega n equal to 1.84. Once you get these two values, then you will find out the damping ratio. Once you get the damping ratio, definitely that will be either under damp or over damped or critically damped. If this is under damped system, then you have to find out the range of damping, that means whether this is lying between 0.68 to 0 or 0 to 0.8. According to that, you just select the formulas TRTP, percentage MP, and TS, and rest of the part is over to you. You can find it out. And this is all about the time response analysis, performance analysis, steady state error analysis, and static error coefficient analysis. Now if you go through these lectures, then definitely there will be no confusion regarding this time domain performance analysis for design of any control system. And there are majority of the questions also coming in the GATE or any other competitive exam. You will find where this type of tricky questions can come, and the different sections already I have discussed in detail, and I think there will be no problem. Thank you.